Okay, so quadratics number 10. Are you ready? Are you thinking about what a quadratic is? Does your brain know by now? Go back through your library, your brain's library. With my own kids at home, when my son Joshua was 4 years old, he would do, your brains at that point are so like a sponge, right? So I would teach him like times tables at 4, right? He could remember anything. You could just show him a flashcard, he'd remember it, right? And I would show him a flashcard and he would say, like 4 times 8, 32. He'd say 32, right? At 4 years old. I thought he was a genius, right? And you are at that. Your brain is just like it'll take anything in, okay? So I asked him, I said, how do you remember that? And he said, in my brain, I see a library with rows of books and there's a little man. And when you show me the flashcard, the little man runs down the aisle, gets the answer and comes back and shows it to me. Like that's what he told me at the age of 4. It's like, oh my gosh, that's genius, right? But he grows up like all of us, and then your brain gets all messed up by life, and then then you turn out like all of us, a just normal person, right? Well, you're all pretty smart. Okay, so on the genius level, but okay, so as you go back through your mind, send that little person back in your brain. What does it find for quadratics? Is it holding anything up? 4, okay. And what does 4 mean? Can you tell me more about 4? 4 what? 4 multiplication steps, right? Pretty good. Is there an easy way to remember the 4 multiplication steps? FOIL. So good, very good. More difficult is when are you using the 4 multiplication steps? What 2 things are you multiplying in that setup? Draw it in the air. Can you see what it is? Did you go like this and this? Is it this? Did you go like this and this? I mean, that's pretty good. Anybody else see that? Did you see that in your mind? Anybody see more? What's in there? What could be a sample of what's in there? What could be a sample? More. Show me more. I like this draw with your finger thing because I can see what you're drawing, shockingly enough. Is that the 4 steps? Are you doing the things here? Yes. What's here, 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 and here, though? The more difficult part. The variables. Can you give me an example? What would be in, for example, this one? You guys okay with that? Yeah. Yeah. And I think if you can remember an example, then your brain is able to, send the little person back, hold up more things, right? And explain this to me. What would you do here, Andrea? Just keep going. What would you do? Yeah. And this is one of the special ones because when 6 times 6 multiplied by these x's, one's a positive, one's a negative, and the center term disappears. You pulled up, your person back there pulling up information from the library stacks. This one's pretty interesting. This is one of the special product ones, right? So this lesson is merely going through the idea that when we graph, we're using intercepts to find out how to graph this, right? So we need to equal 0 here. So I like all that. I think that's good. If you're getting this much in your brain and you can retain this much over time, this will help you a lot. By the way, what's the name of this here? It has sort of an overall name. A what? What is this? It's got nomial in it. It's a binomial. Yes, so what we're doing, what I'm going back to is, you're saying the 4 multiplication steps, it's true, but what you're multiplying is 2 binomials. The 2 binomials make up those 4 pieces that end up in the 4 multiplication steps that go down the road to produce this trinomial. That's a quadratic, fair enough? Yeah, and if you can remember all this process and have an example in your head, you're doing really well. I think this is what you're kind of trying to do after all this, right? So there's more, all right? What shape does a quadratic produce when we graph it? Good. Okay, draw it with your finger. draw it with your finger. Are you guys with me? Draw the shape in the air. Draw the shape in the air that a quadratic produces when you graph it.
When you write quadratic down, you always pay, like you could pay attention to the U and that's how you remember it. Or that's how I remember it.
That's very interesting. Wow, okay, that's kind of genius. Did you hear what she said? She said when you write the word quadratic, if you can focus on the U, that's the graph it makes.
It's the same thing with linear. Like linear is just a line.
And so what do you focus on with linear?
The line, or like if you draw.
Which, are you telling me you focus, like, ooh, that's a line?
Yeah, like it's
Really?
Yeah.
Okay, that's genius. I mean, if you can do that kind of stuff in your brain, you're really helping yourself out, right? And I think it's different for all of you. Try to push yourself to come up with something that means something to you, right? But yeah, what's the graph look like? It looks like a U. Fair enough? Okay, so I like all that. I think you're on the right track with all that. And these lessons will keep challenging you. Go back to this idea of intercept, an intercept form, right? If this is, let's draw, this is our famous X and Y. Is it always that way? Or do they change it? They never change it. Always X and Y. At some point as a student, I learned that it was always X here and always Y here. And once my brain understood it was always that way, somehow it was easier for me. I don't know why before that I thought it could change, or maybe they were just making it up as they went. No, it's always X, always Y. What's that third dimension called? If it comes out like this at you, what's the third dimension? Right, there's two dimensions. There's dimension 1, horizontal, dimension 2, vertical, and the third dimension is coming out at you. Right, remember the 3D movies? The third dimension looks like the movie's coming out at you. If this is X, this is Y, what's the name of the third dimension? Trust yourself. Yes, and that's how you graph on this. But I'm asking for that third dimension name on this whole setup, because this is like a construct, right? You know what a construct is? You ever see The Matrix? It's too old of a movie? See some shaking. No? So what I'm getting at with this is just simply Z. Does that make sense? Dimension 1, X, dimension 2, Y, dimension 3, Z. That's the one that comes out toward you. Does that make sense? That's all I was going for with that. Okay, anyway, kind of off topic anyway. But let's talk about the idea of an intercept form. Where does the U intercept the different axes? Because that's how we graph this. What does the word intercept mean to you? Where it crosses. Anything else? Who wants to add to it? What's the word intercept mean? Where it crosses. So if there's something in here and it crosses like this, right? Where is it crossing the x-axis? And where is it crossing the y-axis? So that makes sense that this would be called an x-intercept. Fair enough? Same with this one. And what's this one called?
The vertex.
Yes, if the vertex, now the vertex is where the parabola changes directions, but where it crosses the y-axis is what I was going for. Fair enough? The intercepts, this idea of intercepts, and that's sort of the big picture graphing of this U, otherwise known, we better use the real name for it. What's the real name? Yes, yes. How do you spell it?
P-A-R-A-B-O-L-A.
Everybody say parabola. Did you remember it that way? Because you kind of spelled it P-A-R-A and then B-O-L-A. Did you remember it that way? So when you have next year your next teacher, don't say parabola. You're going to say parabola. Everybody say parabola. That's the U, okay? And I think this is genius. That's how you remember it. But don't forget this thing too, right? Go keep your brain moving down the track. You want to get more detailed. I don't know why I put that dot there. But that's in my brain, parabola, right? That's how I spell it. Okay, so I'm getting to intercepts. of my parabola, I've got an x-axis and a y-axis, and I want to know where it's crossing those axes. And if I can put in points here, I can pretty much draw this shape, and I can graph this thing very quickly. So using intercept form is talking about where this is crossing those axes. Can you tell me where it crosses the axes? From what you've done so far? This is lesson number 10. We've done it before. Where's that person in your brain running back into the library stacks, looking for an answer? You've got a specific parabola. Okay, go to Desmos right now. Everybody pull up Desmos really quickly. Do it as fast as you can. Go to desmos.com, click graph, and I want you to type this right into the first box. Just type in parentheses x plus 6 parentheses parentheses x minus 6 parentheses equals 0 and see what it does. Type as quickly as you can, go as fast as you can, go there. Go quickly. Oh, you don't even need an equals 0. Look at that. Okay, from the graph that comes up. Good, keep typing. Good, parentheses. Just, yeah, you can do the keyboard there, x plus. You can type it also. It's not faster to use those plus minus keys. Parentheses. Good, x minus 6, are you going? Are you going, are you going? Palmer, are you going? And you know where, well, I hope you know where I'm headed with this. I want to know what the actual x-intercepts are. Can you look at your graph and see what they are?
6 and 8
Positive 6, right here, is a point. Can you click on that and see it show, like I think it'll say how far out on the x it went and how far y. So it's 6 comma 0, right, when you click on it.
Yeah.
And when you click on this one, it says negative 6 comma 0. In parentheses, because those are coordinate locations. X comma y, right? X comma y is our old format. Here's this one here. Okay, look at our setup, and this is going to be a little bit deceiving. How do you get from here to here? Because did you need to graph it on Desmos to know that it crosses at 6 and negative 6? You shouldn't. You may at first, right? I mean, rely on what you got to do to get there. But after a while, you need to know that, hey, this does. What's the actual mechanics behind it? So this gets down to a little bit more complicated, but nonetheless, you've been through it before. For two things to equal 0, A times B equals 0. What must A be? What's a value for A? It has to be for A times B to equal 0. What does A have to be? 0? Okay, so this has got to be 0. What's B got to be? Any number or?
0.
0 also. Because this could be any number or 0, right? So the 0 property of math says if two things multiplied equal 0, we have to test them both for 0. Because if either condition exists, this thing will equal 0. If A is 0, doesn't matter what B is, you'll produce 0. So we're going to have two answers here, right? We're going to take this one, A, so this whole thing's A and this whole thing's B. We're going to say x plus 6 equals 0. We want to know what value x is to produce, when added to 6, to produce 0. Subtract 6 from both sides. X equals minus 6. So that's one of your options. That's where this one comes from here. Notice it's the x plus 6 in the binomial that produces the minus 6 intercept. It switches. Does this make sense? You've seen this before, but do you see it again? Did you catch that? Very? A little bit complicated. Notice it's the binomial that has x plus 6 in it that produces the intercept. That's minus 6. In other words, because of the 0 property rule, it reverses, because you want to know what number am I adding to positive 6 to produce a 0 for this? Well, it has to be a negative 6, so it's this one that produces the negative 6 root. Likewise, this one's going to switch. What number do I plug in for x to make this to 0? It would have to be a positive 6. This is the one generating this root. Right? And I like your example a lot, but I probably should have switched these to different numbers. I probably shouldn't have used both as 6, right? I should have done that and been a little bit more forward thinking, so your brain could see a little bit easier which one was producing which root, right? That would have been a better example probably. Okay, so that's it. You're going to look at a lot of these examples in the practice problems on Schoology. You're going to look at it like this and go, hey, where are the two roots? And basically speaking, you're going to put these guts of the binomial equal to 0 and solve, and that's going to be a root, and do it with both, and you get the two roots of where that parabola crosses. What are your options, by the way? This crosses how many times? 1, 2. What if the parabola is like this? How many times is it crossing the x-axis? Well, if I drew it right, I want to draw it so it touches, but doesn't cross. So how many times does it touch? Just 1. That has 1 root. Okay? And is there another condition where the parabola is up here? Doesn't cross at all. It's called no real roots. Why? Because it's got roots. They're just imaginary. The fun part of math. It starts to become imaginary. That's really the name. I feel like Natalie's looking at me. It's like, really? They're imaginary? They really are imaginary roots. Okay. Let's end it.